Okay, welcome everyone to the RL Theory seminars. I've shared the slides in the chat for anyone that wants to follow along. And so the way these talks work, just like a quick refresher, the talk goes on for 50 minutes. That's 50 minutes or 55 minutes around there. And throughout the talk, feel free to ask any questions. So you can just like unmute, ask the speaker, or if you want to, you can just ask in the chat and then I'll unmute and ask the speaker that question. At the end of the talk, there's like an extended Q&A session, so you can ask your longer questions if you want to wait till the end. And today with me, we'll have Non co-hosting and asking other technical questions to Ayush. And so today our speaker is Ayush, and Ayush is a postdoc working with Professor Sasha Rockland at MIT. He completed his PhD from Computer Science Department at Cornell University, and I guess he's interested in interactive learning, stochastic optimization, machine learning, and, well, reinforcement learning as well, obviously. So today, he'll be our presenter, and you can go ahead, Ayush.
Great. Thanks, Lad. Cool. So please feel free to stop me anytime during the presentation. We'll have waves of like technical and non-technical stuff in between. This is joint work with Yifei Zhao at UC Berkeley, Yuda Song at CMU, and Wen Sun at Cornell. Let me just give a sketch of what the talk will be, and then we can go over some introduction. So after introduction, I will go into the problem setting. Then I will describe the algorithm, followed by its theoretical analysis, and finally discuss some experiments. So let me just quickly delve into introduction. Over the past few years, there have been many successful stories of empirical RL. And there is this general belief that rich function approximation, along with RL, can work well for various problems. And there are various nooks and crooks in this claim, but we can make things work in practice. And on the theory side, our goal is to develop actually provable algorithms that work for MDP with large states and action spaces and work well in practice. And under this motivation, there are two main lines of work. One is model-based RL, where we try to model the underlying dynamics and so on. And the other is model-free RL, where we try to model the value functions and so on. And the focus of this talk will be on model-free RL. Now, there are various approaches for doing reinforcement learning in the real world in the model-free RL setting. The first approach is that of online RL. In the online RL setting, the RL algorithm collects all the data that it needs by interacting with the environment. And because the responsibility of collecting the data is on the agent, it has to balance exploration with exploitation. However, exploration could be very challenging in real-world problems. And on the theory side, we have been developing a lot of insights and algorithms for online RL that work with general function approximation. While there's a rich line of work in understanding statistical efficiency or sample complexity of online reinforcement learning under various conditions, many of these works are unfortunately computationally inefficient. Here is a picture depicting a lot of different structures that people have explored in online reinforcement learning and the relation between them. And unfortunately, beyond simple models like low-rank MDP or tabular MDP, more general structural assumptions and the corresponding algorithms for these assumptions are computationally inefficient. On the other hand, people have also been looking at on-policy methods for online reinforcement learning. These are algorithms like direct policy gradient, natural policy gradient, PPO, TRPO, etc., which are very simple to define because they directly optimize the cost function of interest, in particular the reward maximization. And they are robust to model misspecification and so on. The algorithm is typically simple, but it's statistically less efficient than the previous methods that we discussed, which exploit the structure more efficiently. And in practice, in theory, we need a lot of strong assumptions to say anything about these methods. In particular, we need assumptions like coverage over the state distribution via start state. So to summarize, in this first approach to reinforcement learning, that is online RL, while we have some theoretical intuition of sample efficiency, typically the algorithms are not implementable in practice. And this is a main bottleneck right now between like the theory practice gap for online reinforcement learning. On the other hand, an alternate viewpoint is to do offline RL, where we start by leveraging, where we directly leverage the data sets that are collected by someone else or some other behavior policy. And this is an interesting paradigm because in real life, we do have a lot of big internet-sized data sets available to us. And the question is, can we directly learn a policy just using the previously recorded data sets without making any online interactions with the environment? While this paradigm looks good in practice, there are many challenges that make it very hard to work in the real world. The two main issues that make offline RL hard, the first one is distribution shift. In particular, we are restricted to the data distribution that is collected in the offline data set. And we have to design algorithms that only return policies that are covered by this offline data distribution. And this has led to a long line of work on understanding pessimism in the face of uncertainty and the implications of pessimism and like when we can do it and so on. However, in general, implementing pessimism under general function approximation can be challenging. Secondly, offline RL is not very stable in practice. If you look at the learning curves for offline RL algorithms, they look very jittery as shown in this picture. And furthermore, we don't even know whether an offline RL algorithm worked or not without actually running it in practice. And there are many hyperparameters. We don't know how to tune them without actually running the algorithm in practice and so on. So there's some component of online interaction that is needed. And pure offline is a bit restrictive. In particular, there are a lot of open problems in offline RL, and it's not clear, even under the commonly used structured in online RL, whether we can do something statistically efficiently or not. So to summarize, there are these two lines of work in RL algorithm design. The first one is online RL, and the second is offline RL. And both have their own limitations, and a major limitation is that of computational inefficiency. In addition to computational inefficiency, both online and offline RL relied additional structures such as Bellman completeness and so on and so forth, which could be hard to happen in practice. Any questions so far? Okay, so what do we do? The solution that we take in this work is that of hybrid RL, where we use both online and offline data in the design of RL algorithm. In particular, the system consists of an online loop where an agent can interact with the real world and collect online data. But at the same time, the agent also has access to an offline data, which it can use for improving its performance. And this paradigm of hybrid RL has actually been looked in various forms. It's very popular in applications. Very famous successes of RL like AlphaGo, robotics, and even like large language models, etc., do use some mixture of both offline and online data in their training. And recently, it has also been studied a bit on the theoretical side, starting from the classical works of Shyam Kakade and John Langford, Drew Bagnall, etc., where they think of offline plus online as having access to a reset model from an offline distribution, to more classical works on policy fine-tuning and using online data to fine-tune an offline trained policy in restricted settings and so on. So one popular work, okay, I should not say popular because this is my own work, but one useful starting point for this paper is our previous work, which we called hybrid RL, using both online and offline data can make RL efficient. And this was the work which rigorously explored hybrid RL setting for general function approximation and provided an algorithm called HiQ that works with general function approximation and only relies on square loss regression. So it is computationally efficient. In particular, this algorithm, when provided a value function class, generates a sequence of policies pi1 to pi t, such that for any comparator policy pi e, the cumulative suboptimality of the sequence of policies that we generated is upper bounded by a polynomial function of the coverage of the comparator policy with respect to offline data, some structural property of the MDP example bilinear rank, the number of iterations, and log size of the value function class. While this previous work explored a general purpose hybrid RL computationally efficient algorithm, the provided result actually has a few limitations. First of all, the way this result is stated, it can only compare to policies that are actually covered by the offline data. In particular, we can only compare to policies pi e, for which this constant C pi e that denotes the coverage by offline data is bounded. In addition to that, while I have not mentioned in the theorem statement, this result only holds when a strong structural condition called Bellman completeness holds for the given value function class, which is not always realistic. And finally, this particular algorithm is what is called an off-policy algorithm, in the sense it fits on the previous data. And without Bellman completeness, such algorithms could be unstable in practice. And finally, you can see from this result that it depends on a dimension D, which characterizes structural assumptions that we make about the problem. And it's not clear whether they are necessary for success in hybrid RL. So the starting point of our work is to ask whether we can circumvent these limitations of previous hybrid RL works. And in this work, we provide an on-policy algorithm that overcomes these limitations and in particular enjoys the best of both worlds kind of guarantee. There's a question.
Yeah. I just have a quick question. Like
Yeah.
You said the previous slide that the algorithm was computationally efficient.
Yes, it's Oracle efficient. Like it uses a square loss regression.
Right.
Isn't the algorithm literally just Q-learning?
It is. Yeah.
Yeah.
Exactly. It's like exactly. It's a fitted Q iteration on both offline and online data.
Right, but if you just had online setting with Bellman completeness, would it still be efficient?
No,
Like you were like, I'm just wondering, like because you basically were saying, I think it is the case that in the offline or the online setting with Bellman.
No. This work. I think this is the case for the work he talked about today. This work is both. You need both online. You need both offline data to have good coverage, and then also online access.
Right, but with only in the online case.
If you run it purely online, there's no guarantee.
No, yeah, I understand that, but I'm not saying that this algorithm, but like in the online setting with Bellman completeness, the algorithms we have are not computationally
You can run
efficient.
golf. Unclear if it's efficient, because you have an extra optimistic term.
Mm-hmm. Yeah, I'm just wondering, going back to like what you were originally saying, which is that in this offline and online setting, there's this issue of computational efficiency.
Yeah.
And then like, I'm just wondering if like, how is it that you combine the two settings and then somehow things become computationally efficient? Or was it that things were already efficient in these?
Yeah. So let me like go again over these things. So typically online RL algorithms require something like optimism.
Yeah.
Which is, we don't know how to do it efficiently. And like in some cases, we actually know that some of the statistically efficient algorithms like Olive, which is a work of Nanjiang, is not efficient even for tabular MDPs, probably. And there are other algorithms that people are developing, but it's not clear how to make them efficient. So it may be efficient, we don't know. But right now, we don't know whether they're efficient.
Mm-hmm.
And offline RL algorithms are generally based on this idea of pessimism, which is also a min-max kind of stuff. And we don't know how to make it efficient as well. So independently, both of these approaches, we don't know how to make this efficient. But in this hybrid setting, what this prior work actually explored is to provide an algorithm that uses neither optimism nor pessimism, but only relies on some square loss regression. In particular, it just fits a Q function on both online and offline data.
I see.
And it provides a computationally efficient algorithm that has some guarantees. Okay.
Yeah.
Now, the important thing to note is while the algorithm is online, the guarantee is more like an offline style in the sense what we compare to is what we have coverage in the offline data. So we can't really compare to anything that does not have a coverage.
Yeah.
Right. So while it uses both online and offline data, the guarantee is more like offline style, and it's not clear like whether it is getting like any of the online aspect in the guarantees.
Yeah.
I
Yeah.
should be more clear about this, but great question.
Yeah. And like if you this is like comparable to the guarantees you'd get in just the purely offline setting, but now it's like better that it is computationally efficient.
Yes. Like it's computationally efficient, and I should also say it's actually very like the algorithm is really just fitted to in both offline and online data. And I see of this as a positive that it's a very simple algorithm. It's not like a crazy like it's very simple to understand and implement.
Yeah. Okay. Thank you.
Yeah. So this work basically overcomes these limitations that we just discussed, that there's a gap between like while we're using both online and offline data, we are only getting an offline style of guarantee. And what we do in this work is we actually provide an algorithm that is best of both worlds kinds of guarantee. In the sense, if you have good offline data, which has good coverage over some nice comparator, and you have offline properties like Bellman completeness and so on, you get a nicer bound. However, you still retain performance and have like an online RL style of guarantee, even when the offline data does not have good coverage or like Bellman completeness does not hold. So this is bridging the gap where while you're using both online and offline data, you actually have guarantees that are of both online and offline style. And we'll come to these guarantees in a bit.
Wait, can you just clarify at the end? You said Bellman completeness doesn't hold or does hold? Because the slide says it
Oh,
does.
sorry, it should be does not hold. My mistake. Yep, does not hold.
And you're gonna get guarantees for this case?
Yeah.
Okay.
Cool. All right, so this is what the main contribution of the work is. Let me now delve a bit more into the technical details. Let me start by describing the setting that we operate in. So we consider the discounted MDP setting, where the MDP has a state space S, action space A, some transition dynamics T, some reward function R, some initial distribution mu naught, and a discount factor gamma. And T and R are unknown. That's why they're in red. And the learner can sample online trajectories from the MDP. So the learner has online access. And just some notation. So in this discounted MDP setting, given a policy pi, the value of this policy pi is defined as the sum over a discounted sum where you have a discount factor of gamma to the t on the reward of tth time step for a trajectory that is sampled using the policy pi under underlying dynamics. One thing I should clarify is in this setting, we assume mu naught, the start state distribution, to be a joint distribution over both states and actions. And this is like common in this like on policy RL theory literature. Okay, finally, just some more notations. So we also define the occupancy measure of a policy pi as the probability of being in a certain state. And then you can discount these probabilities depending on when you see them and so on. Cool. In addition to online access to the MDP, the learner also have access to an offline distribution nu, which is a joint distribution over states and actions, such that the learner can draw an offline dataset SAR S prime using nu, where it first samples S and A from nu, a reward function given S and A, and the next state S prime from the underlying MDP. And when we have access, when we are giving access to an offline distribution, we should typically hope that the offline distribution covers traces of some high quality policies. And finally, we are in this function approximation world where we also assume that learner has access to a value function class that maps states and actions to positive values between 0 and 1 over 1 minus gamma. And finally, some more notation. For any policy pi, we define the Bellman operator associated with this policy pi as t pi, such that for any function in this value function class, the new function that is obtained by applying this operator on this function is defined such that the value of this new function on a state SA is equal to the reward on SA plus gamma times a forward push of the state. Like you look at the new state S prime and A prime and evaluate the function on this.
Small notation issue. After the function has f, it shouldn't be a comma, right? Comma means like a function of that type. It should be like a subset of something. But yeah.
Oh, yeah. Yeah. Cool. Okay. So after describing this problem setting, let me now quickly go into the algorithm that we provide. So this algorithm is a hybrid actor-critic style algorithm. This is a computationally efficient on-policy algorithm that uses both online and offline data. The algorithm has two parts. The high-level sketch, or the first part, is what is called hybrid actor-critic. This is a actor-critic algorithm where it initializes a policy uniformly over the action space. Then for T rounds, it first computes an estimate value function for the current policy using a hybrid policy evaluation protocol. And then using this value function, it updates the policy by using the update as shown in this slide. And finally, we return the policy uniformly at random. The key ingredient in this hybrid actor-critic protocol is this hybrid fitted policy evaluation protocol that uses both offline and on-policy online data and returns a value function estimate ft for q of pi t, where q is the value function corresponding to the underlying policy. Now let me describe the key ingredient hybrid fitted policy evaluation. It's a very simple protocol. It takes as input a policy pi to be evaluated, and it returns k loops of the following protocol. In each loop, it first collects a dataset D on of online samples using the policy pi, where each sample consists of a SA pair, sample from the starting distribution, and Y, which corresponds to a Monte Carlo estimate of the value function for the policy pi starting from SA. Then it collects an offline dataset D off of the form SAR S prime using the offline distribution mu. And finally, given both offline and online dataset, at each iteration, it performs a square loss regression, where on the offline dataset, we fit a Bellman error-like term, as shown here. And on the online dataset, we perform a regression to fit Y or Q hats. And finally, we return the average F that is computed by repeating this process for k iterations.
Ayush, question. So for online, you can just regress onto Monte Carlo rollouts, right?
Mm-hmm.
Now for offline, first of all, you said that you collect data, but I think equivalently you can just assume that some data has been already collected and the sitting there. Well, do you need to? You shouldn't need to collect fresh sample in each route.
Yeah, like I think the simplest way to show this is by collecting fresh samples. But then you can do this like complicated sequential dependence analysis to see.
I don't know. Isn't it just a matter of union bound?
I think it is, yeah.
Right. So if you union bound over all f k minus 1 pi, right? Otherwise, I see. No, I see what's happening. No, you'll probably discuss this at some point. It's like if you union bound, you may run into this issue of exploding complexity of the function class. So like
Yeah, but that's
the
like
rate may be
true
bad.
for all policy gradient style algorithms. That's
Yeah, okay.
But if you have like a bounded function class and you know fk belongs to that bounded function class, you can just do a
There's also
union
pi.
bound over all possible
also
fk's and pi.
You also need a union bound over pi.
You also need a union bound
Yeah,
over pi. Exactly.
Especially for MPG where your pi is like that complicated form, like as iteration goes, yeah, it's but I have my actual question, yeah. So yeah, in Tanyang's PSPI paper also has similar problem. But the real problem I want to ask is different. So so if you do FQE, it requires completeness, but I feel like if, for example, if you have a reset model or if you know the offline behavior policy, you could just roll into that policy and roll out with the policy and then get also Monte Carlo estimate from offline distribution, right?
Yeah, that's more like PSDP style. No.
Have you tried that? Because I feel like that will be quite different because here you will get that the Bellman error will be accurate under the offline distribution. But if you do rollouts, you'll get that the function itself will be accurate. So that will be quite different. But the benefit of doing that is like presumably you can get rid of Bellman completeness.
Right. Let's discuss this. This is interesting. We have not thought about that. Yeah. Okay, so coming back to this hybrid fitted policy evaluation, the key thing to note is that the main computational aspect of this algorithm is a square loss regression over the function class, and this could be implemented in practice for various problem settings of interest. Okay, so putting the two together, a hybrid actor treating algorithm interacts with this hybrid fitted policy evaluation, where at every iteration t, you compute a policy pi t, ask hybrid fitted policy evaluation to compute the value function ft for this pi t, and use the value function ft to update the policy as shown using this formula. Any questions?
I have another question just to get things straight. So why do you need to take the average of fk? Isn't the last iteration usually good enough?
Oh, we actually do need for it's not like in our analysis that's it's important to take average. And actually I'm also cheating with you. Like over here I'm showing an average over all k rounds. We only need to take an average over like some like last k over 2 rounds. Like you need to ignore the first few items.
And any intuition or possibly simple explanation for why do you need that?
Yeah, so okay, for the suffix averaging, we need this because we need to remove the bias that comes from F1 over here.
Sure.
Right, and the reason we need average is because like if you look at this, okay, if you want to measure the Bellman error, it would require both this and this F to be the same.
Yeah, well, right. But so that that's the usual problem. Like if you do the minimax stuff, right? So that'll directly straight give you
exactly.
Oh, I see.
Right. So now because you're doing this thing where you're first like you're using fk minus 1 to estimate fk, what you can show is that once you look at the average iterations, just because like both of these places
because fk is Bellman consistent with fk minus 1, which is consistent with fk minus 2.
Exactly.
So there is a potential other workaround, which is you pretend that this is a finite horizon problem. Actually, like I was actually wondering why don't you actually just do everything in the finite horizon? Because usually for online, finite horizon is much cleaner. So I was a little surprised that you chose to go with discounted. But even if you didn't discount it, you could treat it as if it were like just like unfold the problem for like some h steps, and then you just output a non-stationary Q function, which is fk, fk minus 1, fk minus 2.
Exactly.
Then you automatically get a Bellman consistency, but in that finite horizon problem.
Exactly.
Okay, I got what you mean. Okay,
yeah. Okay, so this is the high-level algorithm. Now we'll move into the theoretical analysis for this algorithm. again, like now I think we are entering into some technical stuff. So please stop me if you have any questions. Okay, so as a part of the theoretical analysis, first I want to provide some additional definitions and assumptions, which are all natural in RL theory literature, but I'll go over them again. So let's start by what kind of properties we need from the value function class that we assume that the learner has access to. So for a theoretical analysis, the first property we need is realizability. And this is in all policy realizability. In the sense, for any policy, we can realize the value function for that policy within our function class, where the error that we measure for this realizability is under the states and actions that are explored by that policy. The second important quantity that will be present in all our results moving forward is this definition of pointwise inherent Bellman error. This is a bit technical, so I'll go slowly. So we say that the function class script f has pointwise inherent Bellman error epsilon be if for any function in this class and policy pi, there exists some other function which approximates the effect of Bellman operator with respect to this policy pi on that function. So in particular, it's the gap between what we get from applying this Bellman operator on the function versus some other function in this class. So we say that the function class has a small or a pointwise inherent Bellman error epsilon be if for any function we can represent its backup within the function class. And just to bridge this with previous things that I've been talking about, when this epsilon be is 0, then we know that for any function we can represent its backup for any policy. In particular, we can also do this for optimal policy. And thus, this inherent Bellman error being 0 implies that the function class is Bellman complete.
Why do you need a max norm error measure? Like usually you can do something like max overall admissible distribution type of stuff, right?
We can, but like in this, like I think like I don't really know whether there's an important difference between the two for our application. And this is just
it's just like I mean the max overall admissible is just more general, right? But
yeah, I agree. Like
is it just but occasionally there are cases where I've seen where people say they can do max, but they don't know how to do like max over admissible. Do you feel like here it's just for convenience? Like if you just swap in max over admissible, like it will just work.
So, from us, it is convenience, but to be honest, we have not tried the other one and like seen whether it breaks down. Like it's the starting assumption.
I don't really expect a problem. Actually, like whenever people say that, I don't even know why they can do that. But yeah, just
right. Okay. So one thing I should mention before I go into further details. So this quantity epsilon be being small implies Bellman completeness or approximate Bellman completeness. But as you will see from our results, we also have a guarantee when this epsilon be is large. So the trade-off between the two worlds that we will discuss soon occurs exactly depending on whether this epsilon be is small or large. Okay, now let's go to the further definitions. So now let's look at the comparator policies that we will be comparing to. We look at this notion of NPG coverage. This is again very classical term that's used in policy gradient and natural policy gradient literature. And for a comparator policy pi e, this coverage C of NPG pi e is defined such that for any other policy in the MDP, the occupancy ratio between pi e versus this other policy pi tilde is bounded by C of NPG. And this is not a super crazy assumption. In particular, if your reset distribution mu naught satisfies good coverage over what you want to compare to, then you do have that this quantity C of NPG pi A is also small. And finally, we need some further definitions about
hold on, Ayush. If you have this, then you couldn't you just run online NPG? Like, why do you still need offline data?
That's great. So that will become clear once I show the results.
Okay.
Okay. So regarding offline data, we need a notion of distribution coverage. So we use the notion of Bellman error transfer coefficient, which is from this previous hybrid RL work. And for a comparator policy pi e, this quantity C of offline pi e is defined as the max ratio between average signed Bellman errors of functions under pi e versus average square Bellman error of function under offline distribution. And while this quantity has been introduced in this prior work, we note that this is smaller than various other notions of offline coverage that are common in offline RL literature, including things like density ratio concentrability, or this feature concentrability that is common in linear MDP. And while one direction is trivial, that this could be like this is smaller than or equal to these quantities by some simple application of Jensen inequality, it can actually be significantly smaller for two reasons. The first being there's no sign in the numerator, so it can actually be negative. And second, the concentrability that we use is actually a reward function based concentrability. So depending on the underlying reward structure, you may be fine with choosing a small value function class that does not require you to pay for density ratio and so on. Okay. The other thing to note about this notion of offline data distribution coverage is that when the offline data is actually realized by some policy in the MDP, which we call as admissible offline data, then this offline concentrability coefficient is smaller than the NPG coefficient that we discussed a few slides earlier. And finally, just to remark, our bounds that I'll discuss soon will actually depend on this Bellman error transfer coefficient of the comparator policy. Some questions?
No, it's just coming on this coverage. Like there's actually a closer relationship to the linear MDP case.
Yeah.
So
Yeah.
if you're in the linear, or actually, as long as you're in the linear completeness case, this version of the coefficient that you show here can be upper bounded by a form similar to the last line, but the target policy you want to cover only appears in its first moment. So it's expectation of phi.
Oh, I see. It's like
Expectation of phi transpose
phi
the
transpose.
inverse of data covariance expectation of phi.
I see.
Yeah. So instead of second moment, which means that you need to cover all directions specified by pi e, you only need to cover the mean direction.
Got it.
Yeah.
Right. Anyways, so also like since we're discussing, like this is the point that I want to keep in mind, that this offline coverage could be smaller than NPG when the offline data is admissible. Okay, so now let's go to the main result that we have all been waiting for. So what are the performance guarantees for this hybrid algorithm that I just discussed? So what we provide is a best of both worlds performance guarantee. And this guarantee is as follows. Suppose we run this hybrid actor critic for t iterations with some parameters. Then first of all, for any choice of comparator policy pi e, the cumulative suboptimality of our algorithm is upper bounded in terms of log number of actions and the NPG coverage coefficient for pi e. However, if offline data has good concentrability, good coverage coefficient C off, and approximate Bellman completeness holds, then you can improve this to replace C of NPG pi e by C of square, C offline pi e. In particular, while we get a typical guarantee from online RL actor critic algorithms, we can improve over these guarantees when offline conditions like approximate Bellman conditions and offline coverability hold. And this is the main benefit of using both offline and online data. And I also want to remark again that this algorithm hybrid actor critic relies on this policy estimation procedure, which only uses square loss regression over script f, so it is computationally efficient given this oracle. So our takeaway from this result is we provide a very simple on-policy algorithm that combines the best of both online and offline data. It enjoys polynomial sample complexity in the relevant problem parameters that I just described, and is computationally efficient when we can do square loss regression over the function class. Let me go into the theoretical analysis of how we get this best of both worlds behavior. The key technical tool that actually uses both online and offline data is this hybrid policy evaluation algorithm. Just to recall, this runs for k iteration, where at every iteration it minimizes a Bellman error looking like term on the offline data and a regression to Q hat on the online data. And because you're minimizing error on both online and offline data, you can show that the returned estimate f hat computed by this hybrid policy evaluation protocol satisfies both on policy estimation error. In particular, it's a good estimate for the Q pi under the data distribution induced by the policy pi, where the estimation error is 1 by root t. And when inherent Bellman error is small, then you also have a small inherent Bellman error on the data induced by the offline data. So the key idea is that this hybrid policy evaluation ensures both an on-policy estimation error guarantee and simultaneously an inherent Bellman error guarantee when the inherent Bellman error is small. And having both of these together is why we could get this best of both worlds in the analysis. So let me quickly go over the proof sketch. So we want to show, first of all, that even when the inherent Bellman error is large, we at least recover some online guarantee that depends on C of NPG by E. And when we have access to online data that are small and the inherent Bellman error is small, we can replace the CNPG by C of pi E square. Let's first go into the first part of this two-step proof sketch. So the key idea in the first part is by following a very simple analysis for NPG algorithm, a very standard one, you can decompose the cumulative suboptimality as sum of two terms, where the first term is an estimated advantage of the policy pi t, and the second is an estimation error for qt with respect to pi t on the data induced by pi t. For the first term, a standard analysis of NPG update rule, in particular the fact that pi t plus 1 is given by pi t times exponent of eta f, ensures that the cumulative sum of these advantages for any SA pair would be upper bounded by log of 8 times t. So the first part is fine. For the second part, note that this is exactly the estimation error of Q of pi t, which HPE algorithm guarantees to be smaller than 1 by root t. So just plugging this together recovers the first result for online, like this online style result. For the second part, where we want to show a benefit of offline data when Bellman error is small, we can again decompose the cumulative suboptimality into three terms now, where the first term is similar to what we had earlier, which is the advantage function of pi t under ft. The second one is an estimation error for q of t. And the last one is an inherent Bellman error of ft under the distribution that is induced by the comparator policy. The proof of this is following very similar techniques to performance difference lemma. For the first term, again, by just noting that this is the same thing as appeared in the online case as well, we know that using the update rule of actor critic algorithms, we can bound this guy by log of AT. Let's get it out of the way. For the second term,
Ayush, hold on a minute. Can you go back to this equation? No. So this decomposition, before you do any relaxation, there's a identity version, which also three terms, and I can recognize the first and the third term, but I think the second one is the Bellman error under d pi t, not f minus q under d pi t.
so an easy way to see this is, okay, let's assume that f does not have any approximation error.
Right, but no, yeah, right. Of course, in that case, like it's all zero. But
Then this is exactly the Bellman error term, I think, that you might be.
no. There is a Bellman error term under comparator, and there's another one under the current policy, but they should be symmetric. I don't know how you get F minus Q here. I think that was my question.
Oh,
I can we'll probably go ahead and we can discuss this maybe after.
yeah. We can let's discuss this after. I can open up the proof and go into more details. Okay. Now, for the second term, note that this is again the estimation error of ft with respect to qt, and using the fact that our HPE algorithm guarantees this to be smaller than 1 by root t. This term is also out of the way. And now the missing term is the last term, which is an inherent Bellman error of ft under the states induced by d of pi e. However, note that the definition of Bellman error transfer coefficient implies that this last term is exactly upper bounded by this c of pi e term times the inherent Bellman error under the offline distribution. Using this relation, we can upper bound this by the inherent Bellman error under offline distribution. And finally, use the fact that our HPE algorithm also operated on offline data. And when the inherent Bellman error was smaller than 1 by t, this term would also be smaller than 1 by root t. So plugging this in recovers the second piece of the proof. And that's how we have both of the parts together. Okay, any question about proof sketch so far? Cool. So far I have discussed a hybrid actor critical algorithm, but notice that while this algorithm was easy to explain, there is a step in this which may not be ideal in the real world. In particular, this depends on this update step needs to compute a partition function, which is intractable when the number of actions is large. And there are techniques in the policy gradient literature to get around this issue by using parameterized policy classes and compatible function approximation. I just want to mention that we also have all of this for our algorithm, but I will not provide much details beyond the fact that the results are very similar and you should look at the paper for the exact algorithm and analysis. Finally, let me go into the experimental part. We also perform experiment on some toy examples and some modifications of toy examples. So in terms of toy examples, we perform experiment on this continuous COM block, which is a H-length MDP, where each time step consists of 3 layers, where 2 states are good and 1 state is bad. And there are 10 actions, out of which 1 action keeps you in good states and the 9 other take you to bad states. And this is a classic example that is commonly experimented on in online RL literature. This is an extremely sparse reward signal because you only get a reward after you take the correct action for H many time steps. And exploration in this problem is challenging. And for this problem, we generate an offline data set where we just collect tuples where we take optimal action for with probability 1 minus epsilon and suboptimal action with with probability epsilon. And we argue that this optimal data set around 30% of the time it actually reaches the optimal policy. We compare our procedure to 2 benchmarks. The first one is this algorithm called RLPD, which is a hybrid RL algorithm, which is a hybrid RL off-policy RL algorithm. And it's state-of-the-art for MuJoCo benchmarks. And the key idea is it optimizes the TD error on both online and offline data instead of optimizing like the kind of error that we did. And we compared to a fully online algorithm called TRPO. And here's the result on this toy problem. We show that our method actually performs better than both of them in the sense that our method can solve combination log up to 50 horizon, whereas the previous ones failed to do that beyond like 15. And then we also performed experiments on non-trivial modification of this continuous COM block, where instead of observing the latent state directly, you get a picture corresponding to these latent states. And there's a difference between the kind of picture that you get for during training time and test time. In particular, we take the CFAR 100 data set and connect every latent state with one class of the CFAR 100 dataset. And during train time, the observations corresponding to a latent state are obtained by sampling an image uniformly at random from the training distribution. And during evaluation time, the observation corresponding to the same latent state is obtained by sampling from the CFAR 100 dataset for that class, but using the test distribution. So there's a difference between the distributions induced during train time and test time. And this just forces our procedure to actually generalize and not like memorize these exact decodings. And here also we show that our algorithm beats both RLPD and TRPO for large horizon problems. And one key observation that we realize why our algorithm is better than RLPD, which is also a hybrid RL algorithm, is because of the nature of losses that we are fitting. In particular, RLPD fits more like a TD loss, and its Bellman bootstrap can be unstable when Bellman completeness does not hold. And in this example experimental setting, because of these images and distribution between train time and test time, we can actually argue that the Bellman completeness indeed does not hold, which explains why RLPD is way jittery in terms of its loss on the critic, whereas ours is much more stable. Okay, so these were the experiments. Let me now conclude by going back at what we discussed so far. We provided a new on-policy algorithm in the hybrid RL setting that obtains the best of both online and offline data. And this algorithm is computationally efficient when given a square loss regression over the function class. And we showed empirically that this performs well in practice. However, the main take-home message that I want you to take from this talk is that hybrid RL is a powerful setting that combines the best of both offline and online RL, and is a good way to develop computationally efficient algorithms. And I would be very excited to see future work, future theoretical work in this direction. And in terms of future work, one problem that I'm particularly thinking about these days is how to do hybrid RL in the agnostic setting, where you only have a policy class and no value function class. And there are various interesting questions in this setting as well. And with that, I will conclude. Thank you for your attention.
Any other questions?
Can you just remind me what this RLPD algorithm was?
Yeah, so RLPD algorithm is a hybrid algorithm. It starts with some offline data, and it runs in iterations. And in every iteration, it has some online policy using which it collects some online data and combines all the offline and online data that it has seen so far and minimizes the TD loss over the data.
What is the reason that the Bellman completeness doesn't hold in this domain?
Right. So what you can show is
so this is just what, like each node correspond to a different each latent state correspond to a different image, that kind of thing.
Yeah, but like because of the inherent complexity of CFAR 100, it's not clear whether the distributions of these rich observations are actually disjoint.
Okay.
So when we tried to learn a decoder, we couldn't get more than 70% accuracy.
I see.
So that is the
even
reason why we
an
expect Bellman completeness to not hold.
This is not even necessarily an MDP.
This is not even necessarily an MDP.
Okay.
Like, okay, it depends. Like, it is an MDP because the training data set size is like small, like the total number of states is small. You observe the state directly. It's not a block MDP. Like, maybe that's what.
But if different latent state can correspond to overlapping distribution of images, then it's not an MDP.
Okay, like I feel like there's a slight gap in the way both of us are thinking. I agree with your point, but what I was just saying is that we were not able to learn a decoder. that does not mean that there does not exist. Like in the sense, like, okay, like being a bit
I see.
philosophical.
You're saying just empirically you couldn't learn a good decoder.
Yeah. Like
But
I do believe that.
maybe it's not over. Maybe it's actually not overlapping, but it's just like learning the classifier is very hard or something.
Exactly.
Yeah.
And I do believe, like, okay, I don't know, like, whether CIFAR 10 is CIFAR 100 is overlapping or not, in the sense, like, if you ask a human, can they actually identify all the 100 classes perfectly, or maybe not. Like, I don't really know.
Yeah. Going back to that question, I think I know what's going on, and maybe this suggests some mild improvement over what you're doing. So in that decomposition, yeah. So I think if you write it as equality, what happens is that in the middle term, it should be the expectation of f minus q under d0.
Yes, exactly.
And you relax it because
D0,
you need d pi t's error for the online MPG result.
Exactly.
So you actually use that same thing, repurpose it here, but presumably you lose like a factor of horizon or something.
Yes.
Right. I mean, one possibility is like maybe you have two separate terms. One is on d pi, one is on d0 alone.
Yes.
Right? Then you get both of them small.
Yes.
So you may improve this a little bit.
Yes.
But this is definitely related to the other question, which I think is more significant, which is exactly about whether you have f minus q guarantee versus Bellman error guarantee, right? Because if, for example, let's assume that the offline data is collected by some behavior policy and you know that behavior policy, right?
Mhm.
Then, as I said, you can get f minus q to be small under the offline distribution.
Mhm.
If you can work with that, then you don't even need completeness. Like, I don't know whether that works, but if you could get that to work, you don't even need completeness anymore. Then the offline coverage result will, apart from some details, will just dominate the MPG result in always, right? Currently, the guarantee is already dominant. The only reason that you still have two results is because MPG doesn't require completeness,
Right.
because the MPG coverage is much worse than the offline version.
Right.
That's what I'm saying. Like, if you can get like just f minus q to work, you could just have like one clean result that actually dominates the MPG.
Wait, so let me just try to understand this correctly. You're saying you don't need like this kind of stuff here?
I don't know how to. I don't. That's the part I don't know. It's like I don't know how to get that to work in the error decomposition part. But
Right.
I'm just saying that it seems like seems close enough, and there's a chance that it could just work.
I see.
I mean, also I think maybe it's cleaner to think of in the finite horizon setting, right? And there are some weird things I did a long time ago, which is like, so suppose you're a finite horizon setting, right? And you roll in with behavior policy and roll out, and then just do regression, right?
Mhm.
Then at every level, your f minus q is accurate.
Mhm.
And then when you do this, but let's say you still want to reuse the current analysis and want to do Bellman error. So one fishy thing you can possibly do, I know that it's definitely doable in infinite norm. I don't know whether it's doable under these like expectations, is that you can actually add up the f minus q error between two levels. And then that gives you an upper bound on the Bellman error.
Mhm.
So infinite norm, it obviously works because you just like the f minus tf, you just insert f and q pi and tq pi, right? And f minus q pi is one term. Then the Bellman operator gives you a contraction, and so I don't know. But anyway, I feel like there's maybe something that is not too hard over there.
Right. I think like one fundamental question that I feel like is very beautiful is the following. I just mentioned it in passing, but I give you a policy class. I give you a reset distribution. I give you samples from the reset distribution. Can you compete with the best policy in this policy class without having any completeness? Right? Because like PSDP and so on are actually developed for this exact setting, but they require this weird like policy completeness.
Yeah, policy completeness, right? It's like your whatever rollout policy you use, the optimal policy should be realized at the previous level.
Right.
Yeah. And that's a good question. I think, yeah, but I have no idea.
It's a very technical question, but I feel like I find it very exciting these days.
Mhm. Yeah.
Yes, other questions?
Maybe we should stop recording.
Yes.
Yeah, I'll stop the recording now.